Welcome back to this course on polymer chemistry. In this lecture 13, we plan to cover the effect of temperature on rate of polymerization and molecular weight, and also we will start a discussion on thermodynamics of chain growth polymerization. Before I start this subject, just recap the subject matter what we discussed in the last two lectures. We discussed the various types of chain transfer reactions possible in radical polymerization and their effect on molecular weight. In principle, that if more chain transfer happen, molecular weight actually gets reduced compared to if there was no chain transfer reaction. We talked about gel effect, and we also talked about the effect of glass transition temperature on the resulting polymer, effect of glass transition temperature of the resulting polymer on polymerization process. Now, let us start. What is the effect of temperature on the polymerization rate and the resulting molecular weight? Now, first let us consider the case of thermal initiation. Okay, we know that in case of thermal polymerization, Rp is given by Kpm Fkd I Kt to the power half. You also know that Xn bar, the number average degrees of polymerization, is given by expression. We have deduced this expression in earlier lectures, so you should be knowing this very well, where B is the average number of initiator residues per polymer molecules. Now, from these reactions, if you look at the equation little carefully, you can find out that if the monomer concentration increases, both Rp and the number average degrees of polymerization increases, which is the molecular weight. If the initiator concentration increases, then Rp goes up, rate of polymerization goes up, but Xn bar or the molecular weight comes down. So, what is the effect of temperature on Rp and Xn is we are going to discuss now. Now, this same expression Rp I can divide into two terms. One is temperature dependent and another is temperature independent. So, if you look at the temperature independent term and put in the left hand side, I can put concentration m f to the power half and I to the power half. Now, this part is temperature independent, whereas the other term, the rate constant Kp Kd to the power half and Kt to the power half, these are all rate constant value. So, definitely they will depend on the temperature of the reaction you are using. Similarly, you can break down this number of degrees of polymerization, number average degrees of polymerization into two terms. One is temperature independent, I can break into two terms. This is temperature independent, and the other term Kd Kt to the power half. So, these are temperature dependent. Now, you also know from our basic physical chemistry knowledge that rate constant can be expressed in form of Arrhenius type equation. Expression where you can write rate constant is A e to the power minus E by RT, where K is the rate constant, A is the frequency factor, frequency collision factor, E is the activation energy for that reaction. This is well known to you guys. So, you know that. So, we can express all the three rate constant Kp, Kt and Kd in terms of Arrhenius equation e to the power minus Ep, where Ep is the activation energy for propagation. Similarly, Kd is Ap e to the power minus Ed and Kt is At e to the power minus Et. Et is the activation energy for termination reaction. Now, in this expression, this is the expression for rate of propagation, and now we know that the monomer is consumed both in initiation process and in the propagation process, but because the monomer consumed in the initiation process is very insignificant compared to propagation process. So, rate of polymerization is equivalent to rate of propagation. So, we are writing Rp as rate of reaction, which is same as rate of propagation, whereas Kp is the rate constant for propagation and Ep is the activation energy for propagation. So, I can take this expression and write this K terms in terms of the Arrhenius equation, or I can simply write ln Rp from that earlier expression m f to the power half I to the power half plus ln Ap Ad to the power, this is Ad to the power half At to the power half minus Ep half Ed minus half Et by RT. Okay, we can write all this from this Arrhenius type expression, and this is this term Ep plus half Ed minus half Et we are writing as the entropy of the polymerization reaction. Okay. So, entropy of the polymerization is combination of propagation, initiation as well as termination. So, depending upon the sign of this activation energy, the rate will depend on the temperature. We can just simply write d ln Rp by dt is plus Er by RT square, if you differentiate this term to find out the rate with respect to the temperature. Now, what is the value of Er? Now, we can, before we talk about the value of Er, we can similarly write from the expression of Xn. If you look at these numbers here, Kp, Kd to the power half, Kt to the power half, here Kd is in the down. So, d ln Xn, which gives you the rate of change of molecular degrees of average degrees of number average degrees of polymerization, as similarly Exn by RT square, where Exn is Ep minus half Ed minus half Et. It is coming from the expression we used in the last page. Now, what is the value of Er and Exn? Now, this will come from the individual values of Ep, Ed and Et. Now, as we know, the rate constant or rate of the reaction is much faster for termination, is the highest rate, and then propagation and then initiation. We can simply write from our that knowledge that E t is should be greater than activation energy of this must be greater than E p, because this is the this is the fastest reaction, and this is also fast reaction where the initiation is a slower reaction. So, you expect that activation energy of the initiation reaction should be higher than the other two. Now, what are the typical values of these E d and E t? Typical values of E d for thermal initiation process comes about 120 to 150 kilojoule per mole. As E p comes on 20 to 40 kilojoule per mole, and E t is 2 to 20 kilojoule per mole. This is the experimental value. Now, that gives you the value for E r around 80 to 90 kilojoule per mole inverse. That means that the rate will increase, rate of polymerization will increase with increasing temperature. If you plot the rate of polymerization with 1 by T, it will be coming down linearly. Now, this value indicates that for every 10 degree rise, there is around 2 to 3 fold 2 to 3 times increase in the rate of polymerization. So, if T goes up, R p goes up, and every decade, every 10 degree centigrade, it will be around 2 to 3 times from the original value. Now, if you calculate the number for E x n, you get around 60 minus 60 kilojoule per mole inverse, okay, per mole, which means that degrees of average degrees of polymerization or the molecular weight will come down as we increase the temperature. So, if you plot with 1 over T, this is the curve for R p and this is the curve for your x n bar. So, this is clear to you that from the experimental values of these activation energies, you can justify that if the temperature goes up, the rate of the polymerization will go up, and similar time the molecular weight or the number of average degrees of polymerization will come down. Now, you can justify these in visualizing this way, that once you increase the temperature, the more and more radical gets generated for a given time. Now, if more and more radical gets generated, then more and more polymer forms, okay, for a given time, and more polymer forms, rate of polymerization increases, and because the radical concentration increased with temperature, the termination reaction also increased. So, as the more termination reaction is going on, the average length of the polymer chains also come down. So, you can justify this drop in molecular weight with increase in temperature and increasing rate of polymerization with increase in temperature by just thinking that with increase you get more number of radical generated in the polymerization medium for a given time. Now, if we talked about the other initiation processes, this was for thermal initiation processes. Now, if we talk about the other initiation process like redox, number 2 is redox initiation. Remember the rate expression for redox reaction, it was Kpm Kd, concentration of reductant, concentration of oxidant, twice Kt to the power half, and xn bar would give you Kp to the power m, Kpm twice B twice Kt Kd redox to the power half. Now, again you can break down this expression into two terms, one temperature independent and another temperature dependent. Temperature dependent terms are the rate constant Kp, Kd and Kt, and same as you can do this and do the same exercise what we did for the thermal initiation, and see what is the value of ER in this case. ER in this case means for redox initiation again would be coming around 40 kilojoule per mole. That is because the ED for this reaction, for this initiation process is much lower compared to a thermal initiation process. That is, we while discussing in the initiation the types of initiation process, we mentioned that redox reaction you can do it at lower temperature. That is because the activation energy for the initiation reaction is much lower compared to a thermal initiator. Now, that gives, if you use the same thing, you will find that ER is coming around, whereas the values for Kp and Kt remain same, okay, or means the values for Et and Ep remain same as the thermal initiation, because they are the same reactions we are talking about. So, if you put all these numbers, you will get that ER coming around 40 kilojoule per mole. So, in this case also the Rp goes up as temperature goes up, but it is not at as much increase as in the case of thermal initiation process. Now, what is Exn 0? If you again put this number, you will find that Exn 0 is about 0 kilojoule per mole, which suggests that there is no effect of temperature on molecular weight for a redox initiated radical polymerization. Redox initiated radical polymerization. Okay. So, what for this type of initiation we found that if temperature increases, rate of polymerization also increases, but the increase is not as much as in case of thermal polymerization, and because the activation energy for the molecular build up is about 0, which means there is no effect of the temperature on the molecular weight of redox polymerization. That is why the redox polymerization are done at room temperature or even sub room temperature, because temperature increase won't affect have no effect on the radical polymerization. And the now let us talk about the third type of initiation, which is that photo initiation or photochemical reactions. Photo initiation. Now, we know again from our lectures before, it gives you phi I A K T to the power half. This is I A. I A is the intensity of light, phi is the quantum yield. You do not see Kd term, because Kd for a thermal initiation process is actually Ed is 0, sorry, this photochemical reaction process Ed is 0, and the other EP and ET remain same. So, if you put ED is 0 and EP ET term or the values from same as earlier, you will get ER is around 20 kilojoule per mole, so as EXN. Okay, which means that in case of a radical polymerization initiated by a photochemical reaction, again the reaction rate of polymerization increases mildly in this case with increase in temperature, and so does the molecular weight. Here also molecular weight increases slightly with increase in the temperature. However, you should remember that the in case of temperature effect of photochemical reaction, this is little more complicated, because the initiators which produces radical photochemically, they also produces radical at a higher temperature. So, if you increase, there will be complications of the which type of initiation is dominating, and so this equation will be combination of a photochemical reaction and a thermal initiation. So, this will be little complicated, but for simply we can if you do it at lower temperature, then that thermal dissociation does not come take effect, then this conclusions will be varied that rate of reaction or rate of polymerization slightly increases with increasing temperature, and the degrees of polymerization or the molecular weight also increases with increases in the temperature slightly. Now, remember we got this expression for rate of polymerization, this, and in case of thermal initiation as well, this expression we got assuming that the reaction is at steady state. Okay. We applied the steady state approximation to find out the concentration of the total radical present. So, these conclusions we just made about the effect of temperature on the reaction rate and molecular weight is valid till the steady state is maintained. Once the steady state is broken, for example, this gel effect, during the gel effect, when the steady state is broken, then this is not valid, these conclusions are not valid anymore, and the effect of temperature will be much more complicated than what we just discussed. So, we also did not consider that there could be possibility of transfer reaction in this case. We just talked about the propagation and initiation, propagation, and the termination reactions. Now, there could be transfer reaction, chain transfer reactions as well. Now, from Mayo equation we have seen how the molecular weight varies with the chain transfer of the polymers, where we can write okay, this is we have in the last class or the lecture before last one, we had seen that if there is a chain transfer, then the molecular weight actually drops as a result of chain transfer reaction, and this 0 is this xn bar is the number average degrees of polymerization in absence of any chain transfer reaction. So, if there is any chain transfer reaction, the actual value of Xn bar will come down, and Cs and other C's, it could be S could be a monomer, a solvent, or a molecules which are added from outside by deliberately or by it present as impurities, and this C stand for transfer constant and are given by the rate constant for the transfer and rate constant for the propagation. So, we can again write same RNA equation and write ln Cs at similar to the earlier cases. Okay. Now, generally the activation energy for transfer is higher than the activation energy for the propagation, which means with increase in temperature Cs goes up, the value of Cs goes up. Okay. From this expression you can see, you can write the other similar to other expressions and well, which gives you E transfer S minus E p by R t square. Okay. From this expression you can clearly see that with increase in temperature, if temperature goes up, these values of transfer coefficient, transfer constant goes up, and if this transfer constant goes up, that means what will happen? Molecular weight will further come down. Okay, so we have seen how you can get quantitatively the average average degrees of polymerization in presence of chain transfer reaction, and from this expression we have seen that if we increase the concentration of chain transfer agents, the molecular weight goes down, and if the chain transfer or transfer constant goes up, then also the molecular weight comes down compared to the case where there is no transfer. Now, Cs value, as we seen from the activation energy for transfer reaction and the propagation reaction, that if temperature goes up, Cs goes up, which means Xn comes down. Okay. So, increasing temperature has two effects. Increasing temperature by itself, even if there was no transfer reaction, it was decreasing the molecular weight, and in presence of transfer reaction is further reducing. So, if you have a transfer reaction going on, then the increasing temperature will affect more, it will decrease the molecular weight more in comparison where there is no transfer reaction going on. Both the cases the molecular weight drop with increasing temperature, but if there are transfer reaction going on, then the drop will be much more compared to situation when there is no transfer reaction. Now, that basically says what the effect of temperature on rate of polymerization and molecular weight for different radical processes. Different means different radical processes initiated by different initiation reaction, as and also in case of the radical reaction where you have chain transfer reactions. Now, let us talk about thermodynamics of radical polymerization. In fact, this is true for any chain growth polymerization. So, we can generalize this chain growth polymerization. Now, we have just concluded that if T goes up, Rp goes up. We just concluded in our discussion few minutes back. Now, does it mean that if you keep on increasing the temperature, rate always will go up? The answer is no, because in this case we have only considered the forward reaction. Okay, we are talking about propagation reaction, whereas there could be backward reaction, depropagation reaction as well. This is Kp and this is Kdp, depropagation reaction. Okay. Now, we do not consider normally the reverse reaction, because the temperature we do for most of the monomers, the reverse reaction is almost nil. That is why we always talk about the rate of forward reactions. So, actually the rate of, so net rate of polymerization would be the rate of polymerization propagation minus rate of depropagation. Now, as I said that in normal case, whatever temperature you use for most of the polymers, this is 0. So, we consider rate of polymerization as the rate of propagation altogether. But if we increase the temperature, at some temperature the rate of depolymerization will also be significant. In those cases, we have to consider the rate of depolymerization also, and if you increase the temperature further, rate of depolymerization also increases, so as rate of polymerization, as we discussed just now. So, at some temperature T, which we call Tc, sealing temperature, this Rp becomes Rdp. So, basically this propagation and depropagation reaction, they reach in equilibrium. So, rate of polymerization reaction, propagation reaction is same as rate of depropagation reaction. If I want to show this in a figure, what we can, so if this is your rate and if this temperature, rate of polymerization or rate of propagation increases with temperature. Now, at some point of time, some point temperature, rate of depropagation also, this is dp and this is p, this is propagation and this is depropagation, also increases. Now, that point, so net reaction, net polymerization reaction, which is Rp net, how will that look like? It will be something like this, okay, because below this temperature the rate of polymerization is higher and then the depolymerization becomes significant, and at this temperature, which is Tc, the net polymerization is 0. That means, if you do not see any change in the concentration of monomer, which means that no polymerization is taking place. If you come back after some time and measure the concentration of the monomer, and you see that the monomer concentration is same as before, which means that monomer is not participating in further polymerization reaction. So, that is the time when the equilibration is reached. Now, let us probe this phenomenon little more. At Tc, you have R Rp is same as Rdp. Now, Rp you know Kp m and m dot, and this will be m dot. Okay. So, what is the equilibrium constant? Equilibrium constant K is Kp by Kdp is 1 by m at equilibrium. Now, at equilibrium I write E because this is in equilibrium. So, I write subscript E for this all this concentration. So, at equilibrium constant is related to the concentration of the monomer in this case only. Now, this is a special case where you do not see the concentration of product is appearing in your equilibrium constant. This is only the reactants, in this case the monomer, which is appearing in the your equilibrium constant value. Now, I can from write few thermodynamic expression. We know del G 0 standard gives free energy change for polymerization, Tc ln K, where K is the equilibrium constant. We can write from this Rtc ln me, and we can write del G 0 P as del H 0 P minus Tc del S 0 P, this side, right side Rtc ln me. This, as you know, this is the standard enthalpy of polymerization reaction, and this is standard entropy of the polymerization, and this is standard state for monomer is considered standard state for monomers are either pure monomer, or 1 molar solution of monomer, whereas for polymer is pure amorphous polymer, or slightly crystalline polymer, or or 1 molar solution of polymer repeat units. Okay, so, what does it del H and del S 0 means? That you take a pure monomer and convert to pure polymer, the associated enthalpy change will give you delta is 0, or you take 1 molar solution of the monomer and convert completely into polymer. Now, the associated enthalpy change will be give you del H 0, and the entropy change will give you the del S 0 of the polymer. Now, we look at this expression, and we can this expression, and let us write from this expression thus ln me is del H 0 P by Rtc minus del H 0 P by R. Similarly, we can write Tc is del H 0 P by 0 P plus R ln. Now, what does these two expressions says that Tc and Me are related, okay, they are not independent to each other. If you change Tc, if you increase Tc, the equilibrium concentration of the free monomer increases, and so as the other thing Me increases, the equilibrium concentration of the monomer increases, then Tc also increases. This is a very important thing, that Tc is not a single temperature, okay, it depends on the composition of your polymerization reaction, okay. It is not that every polymer has a, or every monomer has a single sealing temperature, and this is often misunderstood, that Tc is a single number. It actually depends on the monomer concentration as well. Now, how to sort of read these equations little from understanding every if you can consider every temperature, you can consider every temperature as you can consider whatever reaction you are doing as a sealing temperature. Now, there is always a associated equilibrium value of the monomer. If you start a reaction, if you start, or if at any point of time in a reaction, if M concentration is of the monomer is higher than equilibrium value, then the reaction will proceed till M becomes Me, then reaction will not take place further. That means the rate of propagation will be same as depropagation. So, every temperature there is a associated, for every temperature there is a sealing temperature, there is associated equilibrium monomer concentration. So, if you start or any time during your reaction, if your free monomer concentration is higher than the equilibrium monomer concentration corresponding to that temperature, your reaction temperature, then what will happen? The reaction will continue, propagation will continue till your free monomer concentration becomes as the equilibrium free monomer concentration. At any point time, say you start a reaction with your free monomer concentration less than Me, then what will happen? You fix a temperature for your reaction and you start with a monomer concentration which is lower than the your equilibrium monomer concentration, which means the reaction will not go. Rather, if the polymer chain can be initiated, polymer chains can be broken some place and you get a radical or some active center, the polymers will depropagate, unzip to form monomers, so that the free monomer concentration goes up and gives you the equilibrium monomer concentration. And if your at any point of time, if your monomer concentration is equivalent to your the equilibrium monomer concentration, then the reaction will stop. That means that there will be no appreciable, or there is no change in the concentration of the free monomer. So, apparently there is no reaction going on. Actually, there is a rate of propagation is same as rate of depropagation. So, again one more time let me emphasize that if you every temperature, every your reaction, you can choose any temperature of your reaction and consider that as a sealing temperature. Now, that temperature corresponds to a equilibrium value of the free monomer determined by the values of del H 0 and del S 0. Okay. Depending upon this value, you get the relation between Tc and Me. So, for every temperature there is a Me value, and if your at any point of time your reaction concentration, the monomer of the concentration of your free monomer is higher than the equilibrium monomer concentration, reaction will proceed till the reaction, the free monomer concentration is same as the equilibrium monomer concentration. Let us take an example. Now, for temperature 298 K or 25 degree centigrade, what is the Me for different monomers? Now, Me you can get again, T is given, Tc is given. So, that is your temperature of reaction. You can get it from the values of del 0 P and del S P. If you know this R you know and your reaction temperature you know, then you will get this value of the free monomer concentration at equilibrium. So, that is let us vinyl acetate 1 into 10 to the power minus 9 moles per liter, methyl acrylate moles per liter, methyl methacrylate, styrene moles per liter, and alpha methyl styrene 2.2 moles per liter. So, if you can carry out a polymerization reaction of these monomers at 25 degree centigrade, the reaction will stop, or in accurate sense reaction will reach equilibrium till your monomer concentrations comes down to this level. Okay. So, if you start with the pure methyl methacrylate and do the reaction as 298 degree centigrade, 298 K 25 degree centigrade, then reaction will proceed, polymerization will proceed till the free concentration or the concentration of the free monomer becomes 10 to the power minus 3 moles per liter, which also means that you can never complete a reaction. You can never complete 100% entire methyl methacrylate to the polymer stage, because before that there will be stage where equilibrium, where for any temperature where the propagation step and depolymerization step are same. Now, look at the values of alpha methyl styrene, that is 2.2 moles per liter. Now, the concentration of pure alpha methyl styrene comes about 7.7 moles per liter. So, this monomer will polymerize at 25 degree centigrade if you can. Of course, 25 degree you cannot polymerize because you have to generate, that is very difficult. You have to increase the temperature for the reasons you know. If you can start a polymer, or you can polymerize alpha methyl styrene at 25 degree centigrade, then the polymerization will take place till the concentration becomes 2.2 moles per liter. Once it reaches this value, it will not proceed. Now, it will be interesting to see what is the values for Tc when you start with a pure monomer. That is interesting, because if you start with a pure monomer and if your Tc is your reaction temperature, then the equilibrium value of your free monomer is same as the pure monomer. That means, reaction will not at all proceed. Now, let us put this number for the same monomers, the Tc values. Let me cut this and put this. This is value for equilibrium concentration of the free monomer at which is pure monomer. So, what will be the Tc? For styrene it is 310 degrees centigrade, for alpha methyl styrene is 61 degrees centigrade, for styrene is MMA is 220 degree centigrade. What does it mean? If you start a reaction of alpha methyl styrene from pure monomer at 61 degree centigrade, what will happen? This is already reached, pure monomer is the equilibrium concentration. So, that means it has already reached the equilibrium, that means it will never polymerize further. If you do it a lower temperature, then Me value will come down and reaction will proceed till that equilibrium value of the monomer concentration. If you do above 61 degree, the Me value is even higher than the pure monomer, which means again there is no polymerization possible. Okay. I hope you got this concept of T sealing temperature and how does it influence your polymerization process. So, again every temperature you can consider as sealing temperature. Normally you do reaction at a little higher temperature for say 80 degree or 100 degree. Now, if you do at 80 degree, then you can only reach a polymerization, you can carry out the polymerization till the free monomer concentration reaches the equilibrium value of that temperature. Now, because these numbers are low, 10 to the minus 9, 10 to the minus 6, 10 to the minus 3, which is considered say 25 degree centigrade. Now, if we increase say around this 25 degree centigrade, say 50 degree or say 100 degree, it will come down little bit, it go up little bit, even though the numbers will be very low, which means if you do it at 100 degree centigrade, you almost quantitatively convert the monomers, but there will be always some free monomer remaining, which is equal to the free monomer concentration at equilibrium for that particular temperature. Now, how do you get the values of Tc? Now, we know that again from that expression we just talked about plus R ln Me. How do you get the relations between Tc and Me? If we know the reaction, the values of delta is P and delta S P. Now, what is delta S P sign? Delta H is negative because it is exothermic reaction, pi bond is converting to a sigma bond, and del S is also less than 0 because the monomers is getting tied up into a more ordered state compared to a disordered state. So, if we can plot AM versus E versus 1 over Tc, and from the slope we can, if you know this by experimental process, we can get these values from the slope, and intercept is okay. So, if we know these values, we can get the value for del S and del H, and reverse is true. If we know the value of del S and del H, we can find out the relation between the Me and Tc. Now, each point in this represents a particular Tc and corresponding Me value, okay, which means that Tc is not a singular number, it varies along with your free monomer concentration. Now, how does these numbers del H and del S vary with different monomer. Now, del S is del H you know is basically the difference in the activation energy from the propagation reaction and the depropagation reaction. So, if I plot say energy, and this is your monomer and this is your polymer. So, this difference is your del H. So, anything which stabilizes this energy, the monomer energy, will decrease the difference, and anything which actually increases the energy of the polymer, the produced or resulting polymer, it also will reduce your magnitude of del H. Now, so anything if monomer is stabilized, then del H, magnitude of del H will come down. Now, destabilization could be due to resonance, inductive effect or hyperconjugation, or even by inter-monomer association, okay, or interpolymer association. And if the polymer is strained, then also this goes up, del H comes down. So, that will depend on the structure of the monomers, and we will talk about that more in next lecture. Now, what about del S? Del S is basically a difference between your translational, rotational and vibrational entropy of monomer and polymer. Now, whatever vibrational and rotational entropy is lost by the monomers is actually gained by the polymer. So, it is basically the entropy, the del S value is basically the entropy of changing entropy of the translational entropy of the monomers resulting in a polymer. Now, this translational entropy does not depend too much on the monomer structure. So, we will find that the del S values are more or less independent for every monomer in this chain polymerization. So, we will start next lecture from this this page and talk about more on the values of del H and del S, and how a monomer structure actually determine or influence the value of del H, and which in turn determine the thermodynamic feasibility of polymerization of a monomer. So, we will start from this page in the next lecture.